Hello, and welcome to Statics. We're going to be talking about the center of mass. And in the 13th edition of the textbook by Hibbeler, that would be chapter 9. In the 14th edition, it would be chapter 8. So it depends on the edition of the textbook that you have. There we go. Now, why is this important? Oh, here's a few reasons. The boats can roll over. If we don't watch center of mass, if the center of mass isn't low on a boat, it can tip, just like this picture shows. Eastland disaster of 1915. The center of buoyancy was below center of mass. And by the way, we're going to get into center of pressure later, which has to do with rockets. There's other centers of force. Center of buoyancy is where the water buoyancy is, where is the force centered due to buoyancy on a ship? Where is the pressure centered due to aerodynamics on a rocket? So this idea of center of, they call it CG, NASA calls it CG for center of gravity, which near the Earth, center of gravity is going to be identical to center of mass. So if the rocket gets misaligned from, if it's going straight up and it gets misaligned from going straight up, here's the center of pressure. It will, the center of the moment will tend to right the rocket. It'll tend to put it back on the straight up trajectory. And if it goes the other direction, it'll just right it back the other way. It's kind of like a pendulum. Making cars safer. Here's a Jeep rollover. So the center of gravity is very important for a lot of reasons. We are also going to be talking about center of force, center of pressure in this chapter. The mathematics is nearly identical. I mean, you're using different symbols, but the math is identical. The in chapters 4 and in chapter 7, and that would be in both editions of the textbook, it talks about distributed forces. Well, the calculation to find out where a force is centered in distributed forces in chapter 4 are identical to the center of mass calculations. And the same thing is true of chapter 7, where we talked about the moment and loading curve for beams. Okay, one thing before we move on I want to do is to show you where there's some math reviews that'll really help you with the mathematics of this center of pressure stuff. You'll recognize this as the main website page. Go down to here, there's something called AIDS. Math review, area and line properties, center of mass and moment of inertia. Moment of inertia is next chapter. Volume and solid properties, center of mass and moment of inertia. Let's go to what these look like. Here they are. Here are those files as soon as my computer wakes up. Areas of properties and lines. So it's got all those moment of, we'll get into these later, how we got these. Volumes and solids. So this is areas and lines. Volumes and solids. A disk, for example, and rectangular plate and so forth. Various volumes and solids. Areas and lines. Triangle, we've seen this one before. Okay. And it keeps going. So for a lot of your work, you can just take these formulas. Here's a quarter circle, here's a half circle, and so forth. You can just take these formulas. Looked up in Appendix B. looked up in Appendix C. Appendix A, by the way, is there on the website. It's tables of integrals and stuff like that. Math review, trigonometry. Okay, I wanted to get with that stuff so that you guys knew where to go find it and can get what you need to solve problems. And this is about the time in the semester where you need this information. It wouldn't have helped you a lot earlier in the semester, but this is it. So, when we have several objects, the weight total is just going to be the sum of all weights. Weight is a special kind of force. It's the force due to gravity. And G is the center of gravity, or it'll be identical to the center of mass if little g is a constant. The acceleration due to gravity is a constant, then it will be identical to the center of mass. Little g is radial from the center of the Earth. Now, the radius of the Earth is so big that it looks like we live in flatland. And g, little g, acceleration due to gravity, is, to a very, very good approximation, constant and always pointing down, parallel. All the weights would be parallel. So we use that approximation. When you're in outer space, the International Space Station, flying to the moon, you can't use it anymore. But for ordinary people living here on Earth and building bridges and skyscrapers and things like that, this works well. So the moment about the origin, this is a definition of the center of mass, x bar. X bar times the total weight has to equal the sum of all the moments about an origin. Any point, actually, doesn't matter. X bar will be referenced from that point. Well, here it's expressed in terms of the weights. And this connects weight to mass right here. So solving for x bar, we get the summation over all the particles of the distance from the point of reference. This is the x distance from the point of reference. This is the x distance of an individual object from the point of reference times the object's weight divided by the total weight, which is this, which also equals, for constant g, little g that is, summation of all the particles of the x distance from the point of the x coordinate from the point of reference times the mass of the individual particle divided by mt. Similar expressions for y. We're just going to zoom in on m. Usually we zoom in on the center of mass rather than weight. Okay, now you'll notice that the moment around the center of mass, if the center of mass is taken as your reference point, the moment around that center of mass equals 0. So here's the x-coordinate of the ith particle minus the center of mass, the x-coordinate of the center of mass, and this is from any point in the universe, and of course x bar has to also be referenced from that point. And we can distribute w sub I, the individual weights. So summation over I x sub I w sub I equals x bar w sub t, right there. But we distribute it here, we get x bar times the summation over I of all the individual w sub i's, and that's equal to mt, or excuse me, wt. wt, there it is, wt, summation of all the weights. Well, x bar wt minus x bar wt equals 0, so the moment about the center of mass due to weights is 0. And of course, applied forces can cause different moments. But if you're just talking about weight, an object, asking where its center of mass is, the moment due to the weight's 0. If you put a plate on on your finger at the center of mass, that plate will be perfectly balanced. And I think you guys have seen the plate spinners. And of course, plates fall if the center of mass is not over the stick anymore. Okay, next slide. So we'll get, this is a good end to the video. Basically, this video was introductory. We'll get into the, gee whiz, why is my PowerPoint just seems to be slow as anything. Anyway, we'll get into uniform solid bodies next video.